Welcome back to ME 760 Engineering Analysis 1. So sorry for being absent last lecture. I was in the hospital, as Professor Ken Schultz stated in the lecture last time. I noticed that he covered the rest of the matrices, the definition, then he get in the solution for linear system of linear algebraic equations. So today we will just give the description of how to solve the linear system of linear algebraic equation using the Gaussian elimination technique, and hopefully will be done a little bit earlier this lecture, and we'll continue from next time. So let's proceed and look for the solution for a system of algebraic equation on the form of a11 x1 plus a21 a12 x2 plus a13 x3 up to a1 n xn, and this is equal to p1. And you have the second equation, a21 x1 a22 x2 a2 3x3 plus a2n xn equal to b2, up to, let's say, you have a square matrices. The number of unknowns is equal to the number of equations. So let's say that this is an1 x1 plus an2 x2 and so on up to an xn is equal to bn. So if we want to solve this system of algebraic equation, one of the techniques to solve the system of algebraic equations is called Gaussian elimination, or Gauss elimination. So how we'll do the Gauss elimination? The Gauss elimination technique usually composed of two steps. The first step is called forward elimination. So one, forward elimination, and we will describe in a minute what do we mean by forward elimination here. So forward elimination, usually this technique will allow us to reduce a given system, like this system, a given system of equations to either triangular or echelon form. And usually when you transform the system to triangular or echelon form, this is usually accomplished through elementary what we call it elementary row operations. You knew what's the triangular form for the matrix. So we have, if you remember last time, if you have a matrix like this, maybe you will have the upper triangular form, or, and the rest here is 0, or you have the lower triangular form and everything here is 0. So this is the upper triangular and this is the lower triangular. So this is for the triangular form. So what about the echelon form? So the echelon form has two properties. One, all non-zero rows, all non-zero rows are above any rows of all zeros. So if you have the matrix, for example, and you have zeros, rows with zeros or zeros, all the rows that contains at least one number that's not zero should be above the rows that contains all zeros. So the first property is you have to have all the zero rows that contains only zeros here, and the rows on top of it should contain at least one element that's not zero. So this is one of the properties. The second one, the leading coefficient for the row, leading coefficient for the row, and this is usually we call it the first number in the row, we call it the pivot number. So let's say this is the leading coefficient in the first row, for example, and leading coefficient in the second row. Maybe the row has zeros, so the leading coefficient will be here. So this leading coefficient, or the pivot of a non-zero row, so leading coefficient of a non-zero row of a non-zero row should be strictly to the right of the leading coefficient of the row above it. To give you an example of echelon matrix, 3 by 4, so something like 1, A1, A2, A3, 0, 4, A4, A5, 0, 0, 1, A6. So all non-zero rows are above the zeros row. So this one does not have any zero. It came above this one that has 1 0, and this one came above the one that has 2 zeros. So all leading coefficients or pivot here should be on the right for the leading coefficient for the previous row. So where is the leading coefficient here? 4, because 0 is not considered as the leading coefficient. So 4 come to the right of the first leading coefficient for the previous row, and the leading coefficient here is 1. It came to the right for the leading coefficient for the second row, and so on. So this is called echelon form. So what we will do for the Gaussian elimination is we'll take the set of equations, we'll represent them as a matrix, and this matrix will be called the augmented matrix. Then we'll try to do some rows manipulation or elementary operations, to transform them to either triangular form or echelon form, and then we will find the solution. I will show you the details of the process. So The first thing is the forward elimination, and we show that the forward elimination will lead to the reduction of the augmented matrix to the echelon form or triangular form. The second step is called the back substitution. So back substitution, once you reach to the triangular form or the echelon form, let's assume that you will have, let's say, triangular form, you will have only, let's say, you will have only one element here. So you will use this element here to figure out what's the value for this element, then you will do back substitution to get, we'll have two elements here, so you'll get the second one and so on. And I will show you this in a minute. So this is called the back substitution. So let's go on and try to solve this system here. So the system, usually if you have a system of linear algebraic equation, it will be in the form of A as a matrix multiplied by vector X equal to a vector B. So what are the steps for the Gaussian elimination? So Gauss elimination steps. First one is we will start with the system of equations, the one that we just stated here, A11, A12, up to A1n, and this is go to ANN, AN1 up to ANN, multiplied by the vector x1 to xn equal to b1 to bn. So we build the system of linear algebraic equation. So this is the form A, this is the matrix A, and this is the vector X, and this is the vector B. AX equal to B. Then from here, the second step is to compose what we call the augmented matrix. What do we mean by augmented matrix? It is the matrix that's formed from the combination of matrix A and vector B. So the augmented matrix in this case would be A11 up to AN1, A12 up to A1n, and this is ANN. Then we'll have a straight line like this. Then we'll have B1 up to Bn, and this is the augmented matrix. So we will get the factors here for the homogeneous sets of values, and you will include them in the matrix here. So you have augmented matrix that contains the matrix A, this is A, and this is the matrix, the vector B. And this is called the augmented matrix. And then we will perform what we call elementary row operations. What do we mean by elementary row operations? So if we interchange any two equations or rows, this will not change the augmented matrix. So if we say that this is the first row, and we interchange first row with row number 10. So let's assume that we have 100 rows. So if we interchange 10 with 1, we don't induce any change. Why? Because if you look at the system of the linearly independent equations, you can arrange the equations up to your, for example, preference. Let's write the first equation first, the second equation, third equation, so on. Let's assume that those equations, as Professor Ken Schultz just described last lecture, came from the measurements of the temperature across a cube. And you have equations that govern the temperatures, for example. So A11 x1 plus A12 x2 and so on. So maybe you will perform hundreds of measurements and you will get hundreds of equations. So you will start writing the equation. Maybe you will write the first equation, the second, the third, the fourth. Somebody will exchange the equation ranking or equation, how the equation is written. It does not change the problem at all. So when you change 2 rows or 3 rows or whatever, this will not change anything in the system itself. So the second operation is if you do addition of multiples of any equation, and equation here is represented by row, so any equation or row, so any other equation or row, this will not also, any other equation or row, this will not make any change. So let's assume that you said, okay, I will multiply this by 2, then I will add it to this one, and you have this equation. So this will not make any change. If you multiply the third one, if you multiply any row or equation or row by a constant, this will not change anything. Let's assume that this is A11 x1 plus A12 x2 plus blah 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 up to B1, and you multiply the whole row by 3. What will happen? Because this is the whole equation. This is A11 x1 plus A12 x2 plus A13 x3 up to A1n xn equal to B1, and you multiply by 3. You can again still eliminate 3 from both sides, because this is the right hand side and this is the left hand side. You can eliminate the 3 as if you did not introduce any change to the equation. So those are the 3 main properties or operation that you will be using to do the reduction for the Gaussian elimination technique. So if you interchange the position of the rows, if you multiply any row by a constant, if you multiply one of the equation by a constant, then you add it to another row, this will not introduce any change to the system. Did you understand? Okay, so if we choose those operations to do the reduction, now the reduction will be something like what I will show you in a minute here. Let's assume that you have step number 1. Assume that you have x's, mean here that you have values in the corresponding augmented matrix. So let's assume that this is the matrix at the very early beginning. Maybe one of those positions is 0. So after Step number 1, all what you will do, you will say that this is the pivot or leading element of the matrix. So you will say, okay, let's assume that this is 9, and this is here 7, or here's something like, let's say 3, 2, 1, 0, something like this. So you want to make all the first row equal to 0. So this is 9, and this is, let's assume 3. You multiply this by what?
3.
By 3. So you make this one 9. Then you subtract those two rows from each other. So you will have, this is 1, this one is 0. Then you have, this is 1, so you'll multiply it by 9. Subtract 9 from 9, and this will give you 0. And then you will transform, after the first step, you will transform, after step 1, you will transform it to something like this. So all the rows will be just, will be zeros. So you transform all the rows to be zeros. Then the second step is you will come to the previous matrix and then do the same set of operation to transform it to the following format. So we have 0, then the second process is to have 2 zeros here, and so on. And so on. So after n minus 1 steps, you will end up with augmented matrix in the form like this. So you have so you formed what we call either the triangular form or the echelon form. So you make everything like this. So once you transform it here, you will notice that x's here means that you have values. Maybe the value is 0, maybe the value is in a number. So you will notice that after the transformation, you will end up with, let's say, A11, but instead of A11 from the previous, the starting matrix, it will be A11 prime, because now you have lots of operation that you already performed on the matrix. And this will transform it to another value here, A11 prime, A12 prime, up to A1n prime, and B is no longer B, is B1 prime, up to Bn prime, and this will give you Ann prime, this is A21 prime, A3 prime, and so on, and all those are zeros. So now you reduce the main or the initial augmented matrix to an echelon matrix or a triangular matrix, and you have only one element here at the end. So this element states that ANN prime multiplied by XN is equal to what? BN prime. So what's XN prime? XN BN prime over AN N prime. Yes, and you'll take, this is the A, this is N minus 1, and N minus 1, and this is AN minus 1 N. Yes? So you can have the second equation, AN minus 1 N XN minus 1 plus AN minus 1. This is N minus 1, by the way. AN minus 1 and N multiplied by XN equal to N BN minus 1 prime. Yes? You have only two elements here. So you multiply by those two elements. The zeros here will multiply by the BNs and it will cancel out. So you will end up with AN minus 1, N minus 1, XN minus 1 plus AN minus 1 and N XN equal to BN minus 1. So you can get XN minus 1 equal to BN minus 1 minus AN minus 1 and N XN divided by AN minus 1 N minus 1 and XN. You will get XN from here. Then you can calculate any XI from the equations by just getting XI. It will be equal to 1 over AII prime multiplied by BI prime minus summation of AIJ prime XJ, and this is from J equal to I plus 1 to N. So let's give an example so that at least this will clarify things out. So 9x1 plus 3x2 4x3 equal to 7. 4x1 plus 3x2 plus 4x3 equal to 8. x1 plus x2 plus x3 equal to 3. So first thing, what do you think? What's the first step? Augmented. What's the augmented matrix? 9, 3, 4, 7, 4, 3, 4, 8, and then 1, 1, and then 3. So augmented matrix. Step number 1. Everybody knows how we proceed and obtain the augmented matrix. Do you have any questions? Okay, now we will do the first operation that make the augmented matrix a little bit simple. So if you want to multiply and then add or subtract or do something like this, it's better to do it with this first row, because it is all of them are what? Ones. So it's better to interchange the first row with the third row. Just interchange the position. So we will interchange row 1 and 3. So this will give us 1, 1, 1. Don't forget to bring also the coefficients here, the B, 3. Then you have the second row the same, 4, 3, 4, 8. Then the third row is replaced now by the first one, and we will have this one. So this is number 2. Now, after we interchange the two rows or switch it the two rows, so here is 9, here is 1. So let's start from the lower and proceed towards the upper ones. So how we will eliminate the first? So we need to make it in the form of triangular form or echelon form. So we want to make those, the trick now is to make those what? Zeros. To make those elements zeros, we'll start with this first one. This is 9, this is 1. So we'll multiply this by what? By a 9. Then we'll subtract it from this one. So 9 by 1 is 9, from 9 is what? So we'll have 1, 1, 1, 3. Second one will not do anything. So we'll subtract. 9 from 9 is what? 0. 9 from 3 is minus 6. And 9 from 4 is minus 5. And 9 multiplied by 3 is 27. And 7 minus 27 is minus what? 20. So this is the operation that we did here, is we multiply first by 9. Yes? Then we subtract third minus first multiplied by 9. Now, we want now to do same for the elements here, 4. So we'll do the same. We'll multiply the first by what? By 4, then subtract it from this equation. When you will do this, we'll end up with 1, 1, 1, 3 again. The last row we will not change because we are performing the operation in row number 2. Then 4 by 1 is 4. 4 minus 4 is what? 0. 4 by 1 is 4. 3 minus 4 is what? Minus 1. 4 by 1 is 4. 4 minus 4 is what? 0. And 4 by 3 is 12. 12 minus 8 minus 12 is what? So this is what? This is second minus first multiplied by 4. Now, we want to eliminate this one only. Yes? So that I will have 0, 0, 0, and then I will have the upper diagonal. Okay? Yes?
The second row is a plus 4, isn't it? Because it's 12 minus 8 is 4.
No, we subtract. We multiply 4 by 4 here, then we subtract it from this.
So then...
multiply 3 by 4 is 12. 8 minus 12 is minus 4.
Okay, so the second term, the x2 term should be plus 1 then.
Why?
Because it's 4 minus.
No, multiply by 4, so this will be 4. By 4, this will be 4. By 4, this will be 4. By 4, this is 12. Okay. 4 minus 4 is 0. 3 minus 4 is minus 1. 4 minus 4 is 0. 8 minus 12 is minus 4.
Okay.
So I multiplied by 4, and then I subtract the new line from the second line. Okay? Okay, guys? Now I multiply by what? 6 and add. If you multiply by 6 and add, so this one will not change, of course. First one will not change. Second one will not change. Third one, multiplied by 6. Multiplied by, I will multiply 6 by the second. I will multiply 6 here. Then 6 by 0 is 0. Yes? And actually I will multiply 6 by the second and add the third. 6 by the second and add the third. So 6 by the second and add it to here. 6 by 0 is 0, 0 plus 0 is 0. And 6 by this is what? So I will multiply by minus 6. So it will be plus 6 minus 6 is what? Is 0. And minus 6 by 0 is 0. And here is minus 5, so this will be minus 5. And this will be minus 6 multiplied by minus 4 is 24. Plus minus 20 is 4. So we reach to this final equation. So what's this final equation says? It says that I was able to reduce a set of number of equations to just 1, 1, 1, 0, negative 1, 0, 0, 0, negative 5, multiplied by x1, x2, x3, and this is equal to 3, negative 4, and 4. Now, you will take it from the very last row. So you will have in the very last row 5. How you will multiply? Multiply this by this. So 0 multiplied by x1 is 0. 0 by x2 is 0. Minus 5 by x3 is minus 5x3 equal to what? 4. And the second equation will be negative x2 equal to minus 4. And the first equation, x1 plus x2 plus x3 equal to what? 3. This equation will give me what? x3 equal to negative 5/4. And the second one will give me x2 equal to 4. And the last one will give me x1 equal to okay, negative 1/5. Does it make sense? So it will be just, I know that for the very early beginning it is a little bit confusing, but it is like solving the puzzle words. So when you try to find, okay, a name of an insect, for example, that's composed of 3 letters. So you start looking for stuff like this, and oh, this is this, oh, but it does not match the vertical word either, so you have to search for something else. So it is exactly the same here. you'll start thinking, oh, I want to make the second element in the last row and the third row, make it 0. So what's best? If I use the first row and I multiply by +6 and I add, I change this 1 to 6. If I multiply here by +6 and I add, this is 6 plus minus 6 is 0, but I flip this again from 0 to what? To +6. So no. So it's better to look for those two. So when you multiply anything by 0 and you add it to 0, it's 0. It does not change either this or that. So it's better to multiply by -6 here. So -6 by -1 is +6. -6 is 0. So you transform this to a 0. So let me give you the last part of the today's lecture about the linear independence. Then if we have time, I can give you one more example about the Gaussian elimination technique. So linear independence of a set of vectors. So if we have a set of vectors A1 and A2 and AM, all with the same number of components. Let's say if we're talking about real vectors here in real Cartesian coordinates, for example, they will have 3 components and so on. So A1 up to AN. The vectors will be linearly independent if and only if the set of the coefficients Cj such that the summation of Cj Aj is equal to the null operator here from j equal to 1 up to m. This will hold if and only if Cj's are all equal to 0. So if you have a linearly independent vectors and you want to make sure that they are linearly independent, you either have C1 A1 plus C2 A2 plus C3 A3 and so on equal to 0 only if the Cj's or C1 and C2 and C3 and C4 and C5 are equal to 0. Otherwise, if they are not equal to 0, you will not have the equal 0 equation or equality. So the equality should be not equal to 0. So you will have C1 A1 plus C2 A2 plus C3 A3 up to Cn An not equal to 0 if Cj's do not equal, all of them do not equal to 0. So in this case, they are linearly independent. What does mean linearly independent? You cannot write one of them in terms of the rest of the vectors. And this is, we already stated this previously. When we study the linear vector spaces, we said that how you will know that your vector spaces or vectors in the vector spaces are linearly independent if I can write the set of vectors like this and I will not find the Cj's, all of them equal to 0. So if C1 A1 plus C2 A2 plus C3 A3 plus up to Cn An, they are equal to 0, it is a must that C1, C2, C3 up to Cn, they have to be equal to 0. Otherwise, they are linearly dependent. So if they are linearly dependent, Cj's here should not be equal to 0. Maybe one of the Cj's is not equal to 0. Then we will define the rank of a matrix. We will take this definition of linear independence to define the rank of a matrix. So if I ask you what's the matrix rank, so rank of matrix, and the rank of the matrix is defined as the maximum number of linearly independent rows or vectors. So let's assume I have a matrix A equal to 1, 1, 2, 2. Then 1, 3, 2, 2, 2, 4, 4, 4. What's the rank of this matrix? Look at the rows for the matrix. This row is different from this row, but this row is the summation of those two rows. So in this case, the rank is what? Rank is equal to 2, because the number of linearly independent, you cannot find, what does it mean linearly independent? You cannot find a relation. So let's assume this will be equal to vector A1, and this is vector A2, and this is vector A3. Between vector A1 and A2, C1 and C2, if they are linearly independent, the condition is, if they are linearly independent, C1 and C2 must equal to what? Must equal to 0. And this is true. Could you find anything that you will multiply here, this vector and this vector? So when you add, you have to add A1 and A1 and A2 and A2 to these corresponding elements here. Did you find anything that will find a correlation between this one and this one other than 0? Nothing. There is nothing other than 0 that you will find it here. Yes? But for this one, this is what? A3 is equal to what? 1 multiplied by A1 plus 1 multiplied by A2. Yes? So I can write one of them in terms of the other two. So this line is linearly dependent on this and on this. So in this case, the maximum number of linearly independent rows or vectors here is equal to 2. So the rank is equal to 2. So I will just conclude with a theorem that says if you have A, the transpose of A will have the same, A and its transpose will have the same rank. So the theorem states that A and its transpose have the same rank. And what's the transpose of this one? 1, 1, 2, 2, 1, 3, 2, 2, 2, 4, 4, 4. Again, row number 3 is just 2 multiplied by row number 1. Yes? Yes? Row 3 equal 2 multiplied by row number 1. And row number 4 row number 4 equal to row number 3. So 1, 2, 3, 4. You eliminate how many? 2 rows from this, and you have 4 rows, so the rank is equal to 2. So it's exactly the same. Okay, guys. So we'll stop here and continue next time. Have a good weekend. If you have any question regarding the homework, just email me, and I will email you back the hints if you need any hints about solving the homework.
Will you be in your office today at all?
I have another class. I will leave now. Then I have another class between 1:30 and 2:20. Then I will leave for the day because I'm not feeling well. So I will be in hopefully by next Monday. But if you need anything today, I might look at my email, but definitely during the weekend I will answer your email. Okay, guys? Have a good day.